Right, can you see my screen?
Yes, Miss.
So I'm going to move on to chapter 7b. This chapter, we're going to look at the performance of various digital modulation techniques. So the outlines of this chapter. So we're going to look at the bit error probability for baseband data transmission. Right, this is something that I omitted actually in chapter 6 because I want to put it here and compare with the digital modulation technique. All right, then we're going to look at the bit error rate for coherent detection of ASK, PSK, and FSK signal. And also, we're going to take a quick look at the bit error rate for non-coherent detection of ASK, FSK, and DPSK. All right. So, and then at the end of the chapter, we're going to compare, right, the performance of these three types of digital modulation techniques based on, in terms of their bandwidth efficiency and also energy efficiency. All right. Always remember in communication system, the two major resources that are limited and yet you need to make full use of it is the bandwidth as well as the power or signal here. So the learning outcomes for this chapter are as follow. First one, you need to be able to explain the sources of errors in digital communication systems. All right, then you need to be able to calculate the bit error probability for baseband as well as coherent detection. Yeah, then also you need to be able to calculate the bandwidth requirements as well as bit rate, and you need to be able to compare various digital modulation schemes as well, right? In terms of bandwidth, in terms of energy efficiency, as well as the bit error probability. All right, so these are the three measurement criteria for the performance of digital modulation schemes. Okay, so this slide basically will outline the source of the errors in digital modulation. So the first one, the pulse shaping filter. All right. Remember in the previous chapter we talked about pulse shaping filter that we use to actually shape the pulse, right? Instead of you transmitting rectangular pulses that require infinite bandwidth, we actually limit the bandwidth of the signals by passing the signal through a pulse shaping filters. All right. We also know that the pulse shaping filters, all right, will actually change the shape of the rectangular pulse to more like a sync pulse or half of a sinusoidal pulse. Yeah, and when these pulses are sent through the channel, the channel basically is also acting like a filter, basically like a band pass filter. So again, channel will also smear the pulses. All right, and then you may have some intersymbol interference. All right, that again is going to smear your pulse as well. So as the signal propagate through the channels will also introduce some noises. All right, so this noise will actually further degrade our transmitted pulses as it propagate along the channel. Okay, and then the degree of degradation and noises actually will be, it's the added effect, and you actually further attenuate or even distort the signal or the pulses that we send at the transmitter. So at the receiver side, all right, at the receiver side, the receiver's job basically is to, based on the pulses received, all right, determine whether this signal received represent a binary one or a binary zero. All right. So it then need to actually regenerate the pulses. Yeah. And let's recall the pulse shaping process here. Okay, so remember we talked about pulse shaping filter is basically to remove the high frequency components, all right, in our digital data. Yeah. and so that we can transmit them through the band limited channel. Yeah. So the pulse shaping filter basically is a low pass filter. All right. So again, if we look at these two diagram here, they actually show you two different low pass filter response to a rectangular pulse. Yeah. And the first one is when your T over RC is equal to 20. All right. RC basically low pass, we normally use resistor and capacitor to construct, right, a low pass filter. So T is basically the bit duration. All right. So when the ratio of the bit duration to RC is 20, meaning it's big, so you can see that the output of the pulse shaping filter basically resemble your pulse shape quite well. Yeah. But when your T over RC is small, yeah, then you see that your pulses is actually very much smear already. Yeah. That's because of the slow RC response. So that's how the pulse shaping filter will actually smear the rectangular pulses. Okay, and therefore for input data stream, right, that look like this. So this is basically what kind of line coding is used here. What kind of line code is used here? This is what? Polar, isn't it? Because you have positive pulses and negative pulses. Basically, it's polar non-return to zero, right? Polar non-return to zero rectangular pulses. So if our input data stream, all right, let's say is 101101. So, and these binary streams are typically represented by polar non-return to zero line coding. So this will be the waveform of our binary data. All right. And then with the pulse shaping and then with the channels band limited properties characteristic. So what we're going to have is, instead of a rectangular pulses like this, let's say a binary one in this case, yeah, the pulse will be smear and take this form. All right. And then for binary 0, you will have your pulse that take this form here. Yeah. So basically the resultant channel output is the superposition of all these pulses. All right. Then you'll get this dotted one. Yeah. So this is still for baseband now. We haven't done the modulation yet. Yeah? So this is the baseband signal if you transmit it as it is. Yeah, without modulation. And another sources of error is the intersymbol interference or ISI. All right, and recall I also talked about ISI in the previous chapter. Yeah, ISI occur when a pulse actually spread up, yeah, in such a way that it actually interfere with the adjacent pulses at the instant of sampling. All right. So take for example the first input waveform over here, which we transmit a 1 followed by a series of zeros. So again, what kind of line code is used here? This is what on-off keying, right? And again, it's a non-return to zero on-off keying. Yeah. So if you were to transmit a rectangular pulses like this, and after pulse shaping filter, after going through the channel, right at the receiver, yeah, your smear pulse it may look like this. All right, may look like this, and then at this dotted line actually are the sampling instant at the receiver. All right, you need to actually check whether right at the receiver, right, if you sample at the point of sampling, if there is amplitude there's a certain power, that means this is a binary one, right? And then ideally, if at the instant of sampling, the sample of the pulse is zero, the sample power is actually zero, then that means the binary 0. But in this case, due to the ISI or the smearing of the pulses, at the instant of sampling here, the amplitude of this pulse or at this incoming signal is not really 0. All right. So So again, it depends on the decision-making process. Yeah. So remember what we did in our experiment too. So you need to set your threshold correctly. Yeah. At this instant, if you set your threshold a bit too low, then this pulse, the second sample may be wrongly interpreted as 1 instead of 0. Yeah. Okay. So that is the for this binary streams 1000. Yeah, so the receive pulse response basically again, if you were to perform sampling, yeah, so again this instant may give you error, yeah, because of smearing effect. And let's look at another sets of data here. So here we have binary data 1011. All right, so 1011, yeah, and then each pulse that represent a 1, again, due to smearing effect, yeah, you'll see that at the instant of sampling over here, which again correspond to this one, due to overlapping, so because of ISI, right? So the overlapping effect will actually cause the receiver see the incoming waveform as this. All right, 3 individual pulses, each represent binary 1. All right, because of inter-symbol interference, they overlap, right? And then the waveform is going to look like this. So again, at the instant of sampling, the first one, no problem because the amplitude is quite high, so you'll be correctly interpreted as 1. But the second sample is supposed to be a 0, all right, where we are supposed to sample a 0 amplitude over here, but here because due to inter-symbol interference, you can see the amplitude is not 0. All right, and then the third sample is a 1, so shouldn't have any problem in decoding it. The third sample again is a 1, again we shouldn't have problem decoding it. But the fourth sample supposed to be a 0, but and again the sampling actually will reach a certain amplitude over here. Yeah. Then for another technique of so that means we actually need to sample at the right time. If you actually look at this diagram over here, yeah. So the sampling need to actually perform at the right time. Yeah. If you reach here, then you got no problem. But what happens if your sampling time is not at the best spot? Right. Let's say you sample at this point. You sample at this point. So that means that this 1 and this 0 both have the same amplitude. Yeah. So basically you sample at the wrong time. So at the receiver, it's actually very important to make sure the sampling is performed at the right time. Yeah. Then how do we know when is the right time to perform sampling? So we can actually make use of an eye diagram to actually help us to decide where is the best time to do sampling. All right. So basically, eye diagram will show us the amount of inter-symbol interference. Yeah. So the eye diagram can be viewed on the oscilloscope. All right. So how do we view on the oscilloscope? Basically, we freeze the time sweep on the oscilloscope, and so that the waveform actually overlap on each other. Okay, the incoming signal pulses overlapping on each other, and this is what we call eye diagram. Yeah. And then from here, the best sampling time is actually when the eye opening is widest, which is here at this point. All right. So at this point, so that means we can read a 1 correctly, and we can also read a 0 correctly over here. Yeah. So because here also give us the biggest noise margin, all right, the biggest gap, so we can easily read the 1 and 0s correctly. Okay, so this page show you the Nyquist criteria for ISI's free communication. So Nyquist says that the sampling pulses, all right, must have a magnitude of 1, all right, at the instant of sampling, all right, where I is equals to K. This is when we are going to perform the sampling. And the amplitude of the pulse must be 0 at any other time. All right. And in frequency domain, this corresponds to a series of impulses, all right, with the amplitude RB at the multiple bit rate, all right, f minus nRB. Well, n can be any value from minus infinity to infinity. So that means that we're going to have impulses at a frequency that is equal to the n times the bit rate. All right. And what is bit rate? Bit rate basically is 1 over bit duration. Yeah. So this is what Nyquist say we must do the kind of sampling pulses, the criteria for the sampling pulses to ensure zero intersymbol interference. Okay, so at the receiver side, in order to eliminate the intersymbol interference, so there are these 4 things that we must follow. Right, the first one is we have to sample signal following Nyquist criteria. All right, and then use a line code that is 0 during adjacent samples. All right, again, so in this case, return to 0 line code will actually is sampling. Yeah, and the third condition is use a raised cosine filter to shape the pulse, to band limit the pulse. All right, remember a raised cosine filter? Raised cosine filter will have a 0 amplitude at the next bit duration, right? Yeah, remember what is raised cosine filter? Where the response is actually highest for the current bit. Yeah, but when the next bit is read, is sent, it actually has a 0 amplitude from your previous bit. Yeah. So therefore, if you use a raised cosine filter to shape the pulse, then you guarantee to have 0 ISI or very minimum ISI. Then at the receiver, okay, a filter must be used to undo the distortion caused by the channel. All right, so this filter is called equalizer. Yeah. So that's why at the receiver, you often see the match filter or equalizer filter. So this filter basically is to undo the distortion caused by the channel. So actually it's channel dependent. Yeah. So depending on the type of channel, then you have to design the correct filter. Okay. Then we're going to talk about noise, other noise. Yeah. And for a lot of channels or the channel in real life, the common type of noise or the major source of the noise is actually the additive white Gaussian noise. All right, so additive white Gaussian noise. So what is the effect of this noise? This noise may actually cause the symbol 1. Okay, we actually send a bit 1, but at the receiver is actually mistaken for a 0. All right, or vice versa. Vice versa means I actually send a 0, but at the receiver it was mistaken as a 1. All right, so we call this a bit error. Right, I send a 1, but the receiver received a 0. So that means this bit is now erroneous. Okay, and then the error probability. Error probability is defined as the likelihood of an error to happen in a digital system during the detection process. Okay, error probability. So we're talking about the chances of error. Yeah. Then occasionally noise can take on large positive or large negative value and cause detection error as well. Yeah. Okay, so as far as receiver is concerned, there are 2 cases of decision error. Yeah, because we're only sending binary information. So there are only 2 types of decision errors here. So here is we send a 0, but then at the detector, at the receiver, it actually, at the decision making process, it actually chose a 1. Yeah, and also when a symbol 1 was transmitted, but a 0 was actually chosen at the receiver side. So these are the 2 types of error. Yeah. Okay, so in analyzing the probability of error in additive white Gaussian noise channel, we actually have to look at the probability density function of this of this channel. All right. So the probability density function of a random variable W, all right, in this case, because our signal is either 0 or 1, so your W can be either 0 or 1. So this has a Gaussian distribution given by this equation. All right, so this is the probability density function equation for a random variable W with a Gaussian distribution. Yeah. And in this equation, mu is the mean value, and then sigma is the standard deviation. All right, or the RMS value of the noise. And the area under this Gaussian distribution curve is always 1. Right, I believe you learned this as well from the maths. So using this equation, so when we send a bit 0 with a 0 volt, all right, that means the mean noise, all right, the mean value of the noise, this mu, is actually 0. All right, so we can actually rewrite our equation with FWO. In this case, our W, we can actually replace it with a 0. Okay, F0V basically is 1 over sigma root of 2 pi E exponential minus V square over 2 sigma square, because mu is 0. All right, and then for a 1, okay, we're going to derive the expression for a 1 later on, but let's look at the decision process now. All right, so at the decision process, let's say y is the, okay, y basically is a sample value for y at time t. Yeah, and again, in this case, we are going to take yt being a unipolar signal. All right, unipolar meaning transmitted as 0 volt and one transmitted as A volt. So another term for this unipolar that you might be more familiar with is the OOK. All right, the on-off keying. So now, if symbol 0 was transmitted, then because we don't transmit any voltage, yeah, we transmit 0 volt with the 0. So therefore, the sampled value is only the noise. All right, so whatever that value we sample is only the noise. Yeah. So therefore, the Y will have a PDF of N, which actually consists of 0 mean and the of sigma square. So this is the variance. Yeah. So again, if you look at the PDF, the probability density function of this symbol 0, yeah, the mean is 0, so it's centered at 0. Yeah, and then the probability of error for this 0 to be wrongly, probability of error for this binary 0 is actually depending on when we set the threshold, all right, in our decision making. So we'll talk about that later. And now let's look at the symbol 1. Yeah, when we transmit a symbol 1, right, we transmit as A volt, right? Yeah, so in this case, our mean value for the PDF is actually at A, so it's actually centered at A. Yeah, and then plus noise. Yeah, so now while we have a PDF that look like this, yeah, so the center at noise and the distribution curve is actually Gaussian shape. Okay, so now depend on where we set the threshold. Yeah, so now let's say because 0 we transmit at 0 volt, 1 we transmit at 1 volt. So if we set the ideal threshold, and again in this case, if the probability of 0 and probability of 1 being sent is the same, that means a good threshold is actually at A over 2 here, the midpoint. All right, so that means if we actually send a 0, right, we actually send a 0, And at the decision-making process, if the sampled value is greater than A over 2, so which correspond to area under this curve here, this area here, the shaded area under this curve, that means the receiver will actually make a wrong decision. Yeah, the receiver will make a wrong decision if the sampled value is actually greater than A over 2 when we actually send a bit 0. Yeah, so the probability of error with the 0 bit being sent, okay, now is given by this equation. So we actually express it in the probability density function. So now it's actually the area under the curve. So we integrate this the equation for this Gaussian distribution curve, and then take the limit from A over 2 to infinity. So this is where the error is. So this gives you the area, all right? That is for bit 0 being sent. And what about 1 being sent? So with 1 being sent, yeah, and then with the decision threshold at A over 2, when the y or the sampled value is less than A over 2, then the receiver actually will make the wrong decision. Yeah, when the sample value is less than A over 2, then the receiver will make the wrong decision. So this is where the error will happen. Yeah, so the probability of error with the 1 being sent, yeah, again is given by area under this shaded curve here. All right. So again, to find this area, we perform integration of the PDF. Now our limit is from negative infinity to A over 2 instead. Yeah. Okay. So to actually perform the integration and then to calculate the area under the curve is quite troublesome. So we're going to make use of an easy approach. So the easy approach basically is called a Q function. Right? Q function is actually the tail distribution function of a Gaussian distribution. All right, and this is commonly used in communication engineering to determine area under the tail. Right? If you look at this one, these two curves here, we're only interested in this tail. Right, on the left, on the right hand side. All right, to find the error of for a 0. All right. Whereas for error for a 1, we are interested in this tail on the left hand side. Yeah. So therefore, the Q function basically is a good tool to actually help us to find the error for the probability of error for our digital communication. Okay, so by definition, Qx or the Q of x, all right, is a probability that a Gaussian variable will obtain a value larger than the x standard deviation, and it's given by this equation. Q of x is equals to 1 over root 2 pi, all right, the integral of e minus y squared over 2 dy, all right, in integral with respect to dy, and then the limit is x to infinity. All right, will obtain a value larger than the x standard deviation. So it's x, the limit is from x to infinity. Okay, so the probability that 0 is going to be interpreted as 1 and give us an error is the probability that y has to be greater than our threshold value. Yeah, so in this case, we get the probability of error of a 0 being sent given by this equation, right? Yeah, from here, this one over here, this equation, I just copy it over here. All right, now the next step I'm going to do is I'm going to rearrange this equation, all right, so that it look like the Qx equation. All right, I'm going to convert slightly to make this probability error equation look like the Qx equation. So what I'm going to do is I'm going to assign y as the v over sigma, because you look at this equation, this is y squared, and this is v squared over sigma squared. All right, so if I assign y as v over sigma, So dy over dv will be 1 over sigma, and dv will be actually the sigma dy. All right. So now I rewrite the equation for the probability of error. Okay, now y becomes v over sigma square now become y square. All right. So my dv now become sigma dy. Is this one over here? Yeah. And then now my limit instead of a over 2, which is v, now becomes a over 2 sigma. All right. Okay. Because y is equal to v over sigma. So now this is v, a over 2 is v. So now v become y. When changing to y, then it become the limit become a over 2 sigma. All right. Infinity, you see the same infinity. Okay. And if I simplify this equation by cancelling this sigma with this sigma, then you see that the probability of error, all right, when a 0 is sent, look like this already. Okay, so you can see this equation actually is in the same format as the QX equation. Yeah, 1 over root 2 pi, and then the integral limit from a over 2 sigma to infinity, e to the power of minus y square over 2 dy. So exactly the same. Now the limit is different. And this is x. So this is qx. So my x now is a over 2 sigma. So therefore, I can safely say that the probability of error when the 0 is being transmitted is equals to the q function of a over 2 sigma. All right. Are you following me? I can't see your face, so I really don't know how you're reacting to this equation at the moment. Okay, no problem. So this is the probability of error when a 0 is sent. Right, so actually we can easily compute it using a Q function of a over 2 sigma, right, where a is the amplitude when a 1 is being sent. All right, sigma is the, what is sigma? Sigma is the standard deviation of the noise, all right, in the Gaussian channel. Okay, and then when the 1 is transmitted, all right, when the 1 is transmitted and we get the probability of error given by this equation, right, from the previous slide. So now again, I need to rearrange or convert my equation so that it look like the Q function equation. So again, I'm going to replace v minus a square over sigma square. So in terms of v over, I'm going to take v minus a over sigma and then assign it as y. All right, assign it as y. So in this case, if I rearrange, then my v basically is equal to y sigma plus a. All right, and dv over dy will give me sigma. Right, dv over dy will give me sigma. All right, this is a linear equation, isn't it? So dv over dy will give me the sigma, and therefore rearrange this, I get dv equals to sigma dy. If you have a question, you don't post it in the chat box because I can't see the chat box at the moment. You just on your mind and ask, yeah, and stop me when you need to. So the probability of error with the one being sent now is equals to 1 over 2 pi root 2 pi. Yeah, now from minus infinity to minus a over 2 sigma. Yeah, same thing, same replacement as what I did in the previous one. And then now the equation for exponential equation now is minus y square over 2. Yeah, so now the equation is in the same form as my qx already. But the only problem is my limit. Yeah, my limit now is from minus infinity to minus a over 2 sigma. Yeah, the limit for the q function is from x to infinity. So therefore, I need to find a way to reassign my limit so that it look like the qx function. Yeah. So to do this, let's take a look at the probability of error now. Okay, so I'm going to assign probability of error when a 1 is being sent. That means it's the probability of a 0 being detected when a 1 being sent, right? So this actually, it is the one that give you error, isn't it? So now, at the receiver, right, when we send a 1, there are only two possibilities, right? At the receiver. The receiver may interpret as a 1, or the receiver may interpret as 0. All right. So that means the probability of 0 being detected when a 1 being sent plus the probability of 1 detected when a 1 being sent is actually 1, isn't it? Right? So because there are only two possibilities here. Right? So I rearrange this equation. So they will give me the probability of 0 being detected when a 1 being sent is actually 1 minus the probability of 1 detected with a 1 being sent. Right? This equation basically rearranged, I get this. Okay, so what is the probability of 1 being detected when a 1 being sent? All right, probability of 1 being detected with a 1 being sent basically is equals to, okay, Q of minus A over 2 sigma. Okay, Q of A minus A over 2 sigma. So where does this come about? This come about is actually when I perform this assignment, right, y equals to b minus a over 2 sigma, I'm actually shifting my PDF curve, all right, from being centered at A to being centered at 0 already. All right, from being centered at 0. So that means the probability of 1 being detected with the 1 being sent is this limit over here. All right. The probability of 1 being detected with the 1 being sent is actually area under this white curve, this area over here. All right. So that means this is from minus A over 2 sigma all the way to infinity. Yeah. And the Q function has a property that Q minus X is equals to 1 minus QX. All right. So therefore, if I substitute this into this equation, all right, Q of minus A over 2 sigma is actually 1 minus Q of A over sigma. So 1 minus 1, that will give me the 0. So that give me the probability of 0 being detected with the 1 being sent is Q over 2 sigma. All right, so you can see they are the same. All right, they are the same. I mean, is when the probability of error with the 0 being sent is also Q over 2 sigma. The probability of error with the 0 being sent is also Q over 2 sigma, same as the 1 over here. All right, both error can be actually calculated using the Q function of A over 2 sigma. Okay, so that is for OOK. Okay, this is for OOK signal. Okay, when we send the baseband signal using OOK or on-off keying method. All right, on-off keying method where we send a 0 as 0 volt and we send a 1 as A volt. All right, so that's a probability error for OOK. Now let's look at the error probability for polar signal. All right, for polar signal, all right, recall that we actually send a 1 with a positive amplitude pulse. Again, let's say the amplitude is A. All right, we send a 0 with a negative amplitude pulse. Okay, and then the amplitude is the A as well. All right, therefore the PDF of these two different, or the PDF for 0 is going to look like this, center at minus A, whereas the PDF for positive, for the binary one is going to again this curve, same curve, but now centered at A. All right, and then again for this kind of polar signaling, where do we make our decision? We set our decision again at the midpoint, right? Midpoint between these two amplitude again is at here. So this area under this curve actually will be the probability of error when a 1 is being sent. Yeah. And then area under this curve over here, this tail here, is the chances where the receiver will actually interpret this bit as 1, as binary 1 instead of binary 0. All right, any value that is greater than 0 will be interpreted as a binary 1, and where any value that is less than 0 will be interpreted as binary 0. So therefore, this is the error, the probability of error for these two. Okay. So that means the error will occur when the noise level is greater than A. All right. So when we have a positive noise that is greater than A, that actually added to the binary 0 pulse, then this will cause an error at the detection. Yeah. And when we send a 1, if the noise level is very much here says smaller than minus A, meaning at any value that is less than minus A, then that means that will cause the signal amplitude at the receiver to be negative, and therefore being wrongly interpreted as 0. All right. So this is for polar signaling. Yeah. And now you see our decision threshold here that is actually set at 0. So positive or negative. Yeah. So in this case, then again, we are going to make to assume, right? Assume that 1 and 0 have a probability of P1 and P0. So these are the terms I'm going to use. All right, P1 means the probability of 1 being sent. All right, and P0 is the probability of 0 being sent. So in this case, the probability of error is equals to the probability of 1 being sent but wrongly received. All right, plus the probability of 0 being sent but wrongly received as well. Yeah. So now, if 1 and 0 are equal like this, that means the probability of 1 being sent and the probability of 0 being sent are the same. All right. Then the probability of error with the 1 being sent and the probability of 0 being sent will be symmetrical, and it can be found by taking the Q function of A over sigma. All right. So this is for polar signaling. Okay, another way to actually remember is why is it A over sigma here? It's because the noise will actually, a noise level of greater than A will actually cause the error in the detection. All right, this is for polar. But for OOK, because we set the threshold at halfway here, so any noise level that is greater than A over 2 will actually cause an error in detection. All right. Therefore, the Q function is Q of A over 2 sigma because our threshold is A over 2. Yeah. And for polar signaling, our threshold is set at 0. So from 0 to A, we have a distance of A here. All right. So we have a distance of A here. So actually the noise in margin is actually A, right? So therefore the Q function is A over sigma, okay, without the 2, because our threshold or the noise margin is actually A. Yeah. So that is an easy way of remembering it. So now if you were to plot the Q function curve, all right, with respect to X, all right, basically you're going to get a curve that look like this, decrease exponentially. This is expected, right? Because the Q function basically is a form of exponential function anyway. All right. So what it says is you can see from this curve, this graph is that as X increases, the probability of error decreases. Right? As X increases, the probability of error decreases. So what is X? Remember, X is A over sigma, isn't it? A over sigma or A over 2 sigma. So that means when X increases, that means your A actually increased. Right? or your sigma reduce. But in a channel, normally the sigma is pretty constant. Yeah. So that means if you actually send the signal with a higher amplitude, then the less likely it is the detector will actually make a mistake and cause an error. Yeah. Okay. But again, remember, you cannot send as at a as big amplitude as you like, because there's a limitation to the signal power that you can transmit in any channel. All right. Now, let's compare the performance of unipolar and polar. Unipolar again is actually our OOK that we talked about previously, and both type of signal actually are received with a match filter. All right. So this is a unipolar or OOK baseband signaling. So the is given as a Q function of A over 2 sigma. All right. And the probability of error for a polar baseband signaling, we have found it to be Q of A over sigma. Right. So if you were to plot the curve, right, you're going to see that the you need to learn how to interpret this curve. Yeah. So now, if you actually compare this polar signaling, which is Q of A sigma, with unipolar signaling, which is the probability of error is Q over 2 sigma. Okay. Now you can see that if you actually send the data, if you were to send your data using these two types of signaling with the same power, let's say same power over here. All right, if both you actually use the same power to transmit your binary information using unipolar as well as unipolar, if you compare them, all right, unipolar will give you unipolar, which is this curve over here, will give you a probability of error which is 10 to the power of minus 3. All right, whereas polar will give you a probability of error of about 10 to the power of minus 5. All right. So what does probability of error 10 to the power of minus 3 means? Probability of error of 10 to the power of minus 3 means there will be one error in, this means one error in 10 to the power of 3 bits. All right, because 10 to the power minus 3 is 1 over 10 to the power of 3, right? So it means one error in 10 to the power of minus 3 bits. Yeah. And 10 to the power of minus 5 is actually 1 times 1 over 10 to the power of 5, right? So that means one error in 10 to the power of 5 bits. All right. So which one is better? The lower the better, isn't it? One error in 10 to the power of 5 bits is better, right? So in this case, you can see that the polar baseband signal, all right, will actually give you better performance in probability of error, right, as compared to the unipolar. Okay, if both of them are sent at the same power, are transmitted using the same power or the same A over sigma. All right, which is this one over here. Okay, so that is one way to interpret the curve. The other way to interpret the curve is if you actually want the same error performance for both types of signaling. All right, if you want the same performance for both types of signaling, so that means as far as the baseband, the unipolar is concerned, all right, you need 3 dB extra power as compared to the polar signaling over here, because now you want the same probability of error, right? So therefore, if you use unipolar signaling, you need more power, 3 dB more. 3 dB means what? 2 times more power, isn't it? 2 times more power as compared to the polar baseband signaling. All right, if you want to have the same probability of error for these two types of signaling method. Okay, so what we can see from this graph again is the probability of error will actually decrease exponentially all right, with increasing signal power. Yeah. So if you want to improve your performance in the probability of error, then you can increase the signal power lah. So in this case, actually, if you look at it, you don't actually have to increase a lot. You just have to increase the signal power a bit in order to get big improvement in the probability of error. So in this case, we're going to do an exercise to actually work out the values later. Okay. Any question on this slide? No? Okay, because later in your assignment, you are going to plot this similar curve, and then you need to explain the curve, and then you need to evaluate your curve, discuss it, and then also choose the right modulation techniques for your communication system later on. All right. So make sure you know how to interpret this curve. I'll talk about this curve again when we talk about ASK, PSK, and FSK lah. All right, so let's look at an example. So in this example, we are asked to find the probability of bit error for a polar signal with A over sigma equals to 7.4. All right, so again, this is a probability of error curve here. A over sigma equals to 7.4. All right, so 7.4 is a ratio in volt. So as far as power is concerned, then you have to convert to dB. All right. So converting it to dB, so you take 20 log 7.4. So that is equal to 17.4 in dB. Okay. So the probability error curve normally is plotted with the A over sigma in power, right, in dB form. So in this case, if you actually identify, you need to identify from your curve. So 17.4 is somewhere here. All right, A over sigma of 17.4 dB is somewhere here. And then this will give you error of probability error of 10 to the power minus 4. Okay, if you project the 17.4 dB and then along the vertical axis and find the point of intersection with the curve. All right, so this point, and then if you project on the horizontal side, that will give you the probability of error. Yeah, 10 equals probability of error of 10 to the power of minus 4. Okay, so this means there will be an error in every 10 to the power of 4 bits. Yeah, one error 10 to the power of 4 is what? 10,000, right? Yeah, one error in 10,000 bits. Okay, so if the transmission rate is 10 to the power of 5 bits per second, what is the interval for an error to occur? All right, now I send 100,000 bits in 1 second. All right, so how long does it take for error to be detected, to occur, and then it need to be detected lah, yeah. So now again, we know there is one error every 10 to the power of 4 bits. Yeah, so that means to find the interval for error to occur, we just need to find how long does it take to transmit 10 to the power of 4 bits, right? Yeah. So now with the bit rate of 10 to the power of 5, then the interval is basically take 10 to the power of 4 bits divided by 10 to the power of 5 bits. All right, and that will give you 0.1 second. All right, and then with the same transmission rate, what is interval for error to happen with A over sigma equals to 11.2? Yeah, again for 11.2, convert it to dB, then you get 21 dB. So 21 dB, if you again refer to your curve, 21 dB is here. All right, then you find the point where you intersect with the curve is here. All right, then plot look for the horizontal, go horizontal to look for the probability of error. So this gives you a probability of error of 10 to the power of minus 8. All right, so that means there will be an error in every 10 to the power of 8 bits. So that is 10 to the power 8 is what? 10 million bits, right? No, 100 million bits. Yeah. So what is the interval for error to occur then? So again, same bit rate. Yeah. The interval for error to occur basically take 10 to the power 8, 10 to the power 8 divided by 10 to the power 5. All right. So that will give you interval for error to occur every 1000 seconds. All right. And this is equivalent to 16.7 minutes. All right. So you can see we actually from 7.4 to 11.2, and you look at dB wise, is 17.4 dB to 21 dB. All right, so you increase our signal power by about what? 4 dB, by about 4 dB. We actually improve the error performance by how many times? 10,000 times, isn't it? Right, 1,000 second over 0.1 second, that gives you 10,000 times. Okay, so that is what you need to deduce. All right, so a small increase of about 3.4 dB in signal power improve the probability error by 10,000 times. Okay, and with this, you actually with the bit rate of 10 to the power of 5 bits per second, you actually improve the interval for the occurrence of error from 0.1 second to 10,000 seconds. All right. So instead of having an error every 0.1 second, you only have one error in 1,000 seconds. Yeah. So that is the relationship between the probability of error with signal power. All right, so I think it's a good point to take a break. Yeah. Any questions before I stop for break?
No question.
Yeah, clear. Okay, good. So let's stop for a 10 minutes break. The Q function is used for what? Samuel, do I need to answer this question now? Did you ask this question before I talk about Q function or Q function? Q function is used to find the probability of error. I went through the whole process of equating the probability of error equation with the Q function equation, just to show you that you can find the probability of error using Q function rather than perform integration under the curve. Right? Instead of perform integration under the curve, just make use of Q function to find the probability of error. Yeah. Can. Yeah. Did that answer your question, Emma? Right. Okay. So let's stop for a break, and then we'll come back in 10 minutes. So now is what? 12:04, 12:04, 12:15. Chin Wei Hong, why you so late? Liu Leong Ho also very late. Okay, so let me remind you lah. If you want to join lecture, please join within 5 minutes after the time has started. Because wait for you for 5 minutes. After that, once I started my lecture PowerPoint presentation, I won't stop anymore because it's actually an interruption to my lecture. and I was doing recording, so I really don't want too much interruption during recording as well. All right, but you are free to ask question during when I actually talk, when I actually do lecture. Okay, you please ask question. If you need to stop me and ask, please stop and ask, because those question are could be valid as well, yeah, and could actually help you to understand the lecture. Okay, is everyone back?
Yes, Miss.
Okay, so I'm going to start the second part of the lecture. Yeah. All right, so on this second half of the lecture, we are going to look at the bit error rate or the probability of error for coherent ASK, PSK, and FSK modulation technique. All right, so bit error rate for binary ASK. All right, so now if you look at binary ASK, the received signal actually is same as the baseband signaling. All right, so it's very similar to the OOK baseband signaling. So the amplitude can either be A volt or 0 volt, right? A is for when is to carry a binary 1, 0 volt is to carry binary 0, right? So it's very similar to the baseband, yeah. So therefore, the sampled value YT will actually has the same identical PDF to the baseband, the OOK case, yeah. Therefore, assuming equal probability of transmission of zeros and ones, the decision threshold again must be set at A/2. All right. Then the probability of error for ASK is given by Q function of A/2 sigma. So this is same as the baseband unipolar signaling. Yeah, the baseband OOK signaling. Okay, because the modulation concept is similar. Then about BPSK. All right, BPSK, we actually send the signal using two different phase angles, isn't it? And that results in the amplitude of 1 is positive and the amplitude of 0 is negative, right? So therefore, at the receiver after multiplication, you get your you get your signal back, which is again very, very similar to your polar signaling signal, right? So that actually gives us the same, again, the same probability of error for BPSK, same as the polar signaling. Yeah. Because the probability, the PDF curve again is the same as the polar signaling. Yeah. 0 being transmitted, you have a PDF that's centered at -A. Whereas 1 being transmitted, you have a PDF that's centered at +A. So again, you set your decision threshold at 0, which is halfway. So that gives you a Q function of A/sigma as well. Yeah. So same as the baseband polar signaling method. So that's for BPSK. And then for BFSK, recall that we actually send zeros and ones using different frequencies, right? Yeah. And then for coherent detection, basically we use two sets of coherent detector, isn't it? And so this coherent detector each consists of a filter, a bandpass filter, to actually allow only the frequency of the binary data that we send. Then we multiply it with the local carrier. All right. So in this case, this path is actually decoding or trying to recover a binary 0. All right. So therefore, we multiply with the carrier signal that is the same one used for binary 0 over here. Yeah. Then followed by a low pass filter that will recover our binary FSK signal. Yeah. So now, if you look at these two, each branch basically is behaving like an ASK detector. Oops. All right, each branch is actually behave like ASK detector. So the output of each branch basically will consist of the amplitude plus noise. The amplitude where we send the signal is plus the noise if a symbol is present. If a symbol is not present, then the low pass filter will only passing noise through. Yeah. And if I were to call the noise output at the top branch N0 and the noise output of the bottom branch N1, All right, so each of these noise actually have identical statistic. Now, if you look at output, if a symbol one is transmitted, then we have the output being A plus the noise N1 multiply N0T, right? When a 0 is transmitted, then the output will be minus A plus the noise, the difference between the noise as well. So now the detection threshold, all right, again, we set to 0, yeah, and the noise term here will be N1 minus N0, all right? And you must also remember that this N1 and N0 actually are noise coming from two different channels, okay, or two different bandpass filter, yeah. And therefore, the spectra of these two noises do not overlap, yeah. They actually, these noises actually come from two different channels. So in this case, the variance is added. We need to add the variance, and therefore the noise variance will be double. So what we do is we replace the sigma square by 2 sigma square, yeah, for the BPSK case, and that will give us the probability of error for FSK equals to Q function of A over root 2 sigma. All right, A over root 2 sigma. This root 2 basically come from the variance of the noise being double here. Yeah, and Q of A over sigma here because the amplitude is either A or minus A. So again, in this case, it's same as the BPSK amplitude. Yeah, except for the noise. Yeah, the noise is a bit more as compared to PSK. So therefore, this is root 2 sigma over here to actually represent that the variance of the noise is actually double. Okay, so that's for the BFSK. So this slide actually compare the 5 modulation schemes, or actually 3 modulation schemes with the baseband signaling. All right, so we actually look at 2 types of baseband signaling only, which is the unipolar and polar. All right, so for unipolar, the probability error is Q function of A over 2 sigma, and the polar signaling gives us a probability error of Q over A over sigma. All right, whereas for binary ASK, the probability error is Q of A over 2 sigma, and BPSK is Q of A over sigma. All right, and BFSK is Q of A over root 2 sigma. All right, so if you look at these 5 schemes, yeah, so which scheme actually gives us the best performance? Yeah, if you look at the 5 schemes, which scheme actually look at best performance? Of course, I say here polar signaling and BPSK give us the lowest probability of error lah. So the best probability of error basically means what? The best performance, isn't it? Yeah. If you look at the QX, all right, QX basically will decrease when X increase. All right, that is because, again, the probability of error curve is this one, right? This is your probability of error, and this is your A over sigma. Okay, so probability of error, we can find it using QX, and where your x-axis is actually X. Yeah, so therefore, the bigger the X is, then the better the performance is, because the probability of error is lower. All right, probability of error means the less chances that the detector will make mistake in decoding the binary information. So again, if you look at the term in bracket, which is X, okay, A over sigma is actually the bigger value as compared to A over 2 sigma, and also A over root 2 sigma. All right, so therefore, from this table, it actually shows the BPSK and then polar signaling actually give you the best performance in in terms of the probability of error. Right, so this slide show you an example of a Q function table. You will also get this in your appendix. I actually put this as appendix A. All right, so you need to refer to this table whenever you need to compute the probability of error given the x value. You know the A over sigma, then you can easily find the QX from this table. All right, so we'll learn how to make use of this table in the example here. So now assume the carrier amplitude A is 1 volt and noise standard deviation is 1/3 volt. Determine the bit error probability for coherent detection of ASK. All right, so the first thing you need to do is to write down the equation for the probability of error for coherent detection of the ASK signal. So that is Q over AX, Q over A over 2 sigma, right? Q over A over 2 sigma. So when you use Q function table, bear in mind you don't have to convert to dB. Straight away take A divided by the standard deviation sigma. So A is 1, all right. 2 times sigma is 1/3. That gives you Q of 1.5. All right, so Q of 1.5, that means this X is 1.5. All right, X is 1.5. So you go to your Q function table over here, look for X is 1.5. This is X, this is QX. All right, this is X, this is QX. So where is 1.5? 1.5 is here, isn't it? All right, so X is 1.5, then QX is this, 0.066807. All right, so you get the number from there. So that will give you the probability of error of 0.0666807. Yeah, if you use ASK scheme to transmit the signal, you with the amplitude of 1 volt. All right, and in a channel with the standard deviation noise of 1/3 of a volt. Okay, what about PSK? So for PSK, all right, PSK, the probability error equation is Q of A over sigma. All right, Q of A over sigma. So A is 1, sigma is 1/3. So that means you need to find Q of 3. Yeah, Q of 3. So again, refer back to the Q function table and look for X is 3. All right, X is 3 here. Yeah, X is 3 here. And therefore the QX is 0.0013499. Yeah, 0.0013499. So that gives you the probability of error being 0.0013499. Yeah. And what about FSK? FSK, the equation for probability of error is Q of A over 2 √2 sigma. Right, Q of A over √2 sigma. So now putting the numbers in, that means you need to look for Q function of 2.12. All right, Q function of 2.12. And if you actually refer to the Q function table, you can't find the 2.12. All right, you can only find 2.15 and 2.10. All right, and which one should you use? Always use the lower one again. All right, use the lower one again, because if you use the upper one, you are over guarantee. Yeah. So now our amplitude is 2.12. So I'm going to use 2.10, and that give me the probability of error of 0.017864. All right, 0.017864. Okay, so now let's compare these three then. Yeah. So numbers will also tell you which one give you the best performance. So again, this one, if you convert into the same, about the same one, so I use 3, 1, 2, 3, 3 decimal place. So 1, 2, 3. So that is 66 times 10 to the power of minus 3, right? So this one is what? 1.3 something times 1.34 times 10 to the power of minus 3. All right, this one is about 17.9 times 10 to the power minus 3. Okay, so the smallest number is the one that give you the best performance. So this one is the smallest, isn't it? Yeah. So PSK is give you the lowest error rate, and then followed by FSK. All right, this is number 1, this is number 2, and this is number 3. All right, ASK give you the worst probability of error. Yeah, meaning if you actually transmit using ASK, the probability of error is higher. All right. Okay. All right, now let's look at another example here. In this example, we have a PSK modulation scheme, binary PSK modulation scheme. Noise standard deviation again is 1/3 of a vote. Suppose the bit error probability is 0.000171068. Determine the carrier amplitude. So again, to find this, we have to make use of the Q function table. All right. So firstly, list down the equation for the probability error for binary PSK. All right. So that is Q of A over sigma. Right, Q of A over sigma, and it has to be this number. All right, so you refer back to the Q function table, 0.001078, 0.001078, 30, 0.0, this one over here, 0.001078. Yeah, so this correspond to an X value of 3.7. All right, with the QX of 0.001078, the X value need to be 3.7. Okay, so that gives us the A over sigma must be 3.7. Yeah, and now a sigma is 1/3, so that gives us the A is equals to 1.23 volt. So that means we need to send the signal with the carrier amplitude of 1.23 volt. Okay, next question. What is the carrier amplitude required to improve the bit error rate probability by 2000 times? Right. So to improve the bit error probability by 2000 times, you don't multiply the bit error probability by 2000, you divide it by 2000. All right, because the lower is improvement. All right, so you need to find the new probability of error, which is the current one, divide by 2000. Yeah, and that gives us 5.39 times 10 to the power of minus 8. Right, so now we go back to our Q function table, and we find the QX of value 5.39 times 10 to the power of minus 8. All right, so let's get back to Q function table. 5.39 times 10 to the power of 8. All right, so you can see now here, this value over here. Okay, maybe let me highlight over here. 5.3 will give you 5.79 times 10 to the power minus 8, and 5.35 will give you 4.3977 times 10 to the power minus 8. All right, ours is what, 5.38, isn't it? So it's somewhere in between, right? Somewhere in between, isn't it? Then you need to estimate, right? So it's about 5.30 or 5.31. All right, 5.0 or 5.31. So I think I'm safe to use 5.31. All right, if you're not worried, you can use 5.3. No problem with that. Okay, so so I'm going to use 5.31. So A over sigma is about 5.31. So that means my A needs to be 1.77 volt. All right, now I need to send, in order to improve the bit error probability by 2000 times, right, I need to send the BPSK signal with a carrier amplitude of 1.77 volt. All right, so if you compare the previous amplitude with the current amplitude, right, I only increased by about 0.5 volt, right, 0.54 volt in the carrier amplitude. But actually I will achieve an improvement in the probability of error by 2000 times, right? So basically you just increase A slightly to get a big improvement in your probability of error lah. That's due to the exponential nature of the curve. All right. So now that is for, so far I've covered the bit error rate for coherent detection of ASK, PSK, and FSK. So let's move on to look at the bit error rate for non-coherent. All right, for non-coherent detection of ASK, PSK, and FSK. For non-coherent demodulation, so just a bit of discussion on comment. So far for coherent detection, we can actually get the probability of error equation quite well, but we also need to take note that coherent demodulation or coherent detection assume there's a perfect synchronization, all right, between the receiver and the transmitter. And however, we also know that this is actually very, very difficult in practice, all right, especially when the channel is dynamic. Yeah. So when the carrier phase is actually and okay, all right. So to get accurate phase synchronization, basically you need to know the carrier phase well, right? So now in a dynamic channel, the phase synchronization actually is very difficult because of the propagation delay, all right? And then there could be some frequency shift caused by your channel instability. Your local oscillator may not be as stable, and you have some strong noise that may actually alter the phase of the signal. Okay, so for coherent detection, if the channel is actually short distance, then you should not have any problem. But if the channel is a long distance channel, then you will have problem where the performance of coherent detection will actually be degrading quite seriously. Right? So so depend on the channel. So in some channel, right, where it's challenging and the carrier phase may not be known, then you have to rely on non-coherent detection. All right. So for non-coherent detection, as the name suggests, there is no need to know the carrier phase. All right. The circuit is actually simple, right? We actually looked through some of them already in previous slide, chapter 7a. So here, circuit is simpler, but it's very difficult to analyze. So I'll just give you the some short analysis. All right, so here, first one, for the non-coherent demodulation of ASK signal. All right, so we make use of the envelope. All right, so for ASK, where we send a 0, we don't send any carrier amplitude. Carrier amplitude is 0. So basically, the envelope is only the envelope of the noise. All right, and when we send a 1, so basically the envelope will be consist of the amplitude of the carrier plus the noise. All right. So if you look at these two equation for these two envelopes, when a 0 is being sent, the envelope will have a Rayleigh distribution. Yeah. And then when a symbol 1 is being sent, the envelope will have a Riccian distribution. All right. So this gives us the final expression for the probability of error for non-coherent detection of ASK is about, all right, approximate to be half of e to the power of minus a square over 8 sigma square. Yeah. And how is this compared to Q function? All right. So if you compare to the coherent detection, right, the probability of error of SK is actually Q of Q function of A over 2 sigma, right? So Q function of A over 2 sigma with the same A over sigma value right, it's going to give you a smaller number compared to this equation over here. All right, so this is for coherent detection, and this is for non-coherent detection. This one over here, this one is for non-coherent detection. All right, so non-coherent demodulation or detection actually will have a slightly worse performance in terms of probability of error as compared to coherent detection in ASK. Yeah, and however, if your A over sigma is large, okay, for large signal to noise ratio, all right, these two number is very close to each other. All right, this number very close to each other. Therefore, the non-coherent detection method can work fairly well as well. But that is only true for large signal to noise ratio. Then we'll take a look at the non-coherent demodulation of FSK signal. All right, FSK signal demodulation, as we talked about previously. All right, again, we use two circuits to actually recover our signal. All right, one for 0, one for binary 1. So instead of using coherent detection here, after the bandpass filter, we use the envelope detector. All right, to actually see whether there is an energy or not at this path, right? So the output of the bandpass filter with the one being sent, all right, is going to be, okay, Y1 path. Y1 path is the one that we use to detect 0. And this path is actually used to detect a 1. All right, so when symbol 1 is being sent, Y1 is going to just detect noise only. All right, whereas Y2, the path at the bottom here, this is Y2, this is Y1. All right, so the Y1 basically, well, Y1 after bandpass filter, sorry, Y1 is here, and then Y2 is here. All right, so Y2 will consist of noise as well as the signal component. All right, the carrier component for binary 1. So again, if you look at the distribution of the signal for these two paths, all right, so this one only consists of noise. So therefore, the distribution is Rayleigh. And the second path is, again, it has noise as well as the carrier component. So the distribution is again Rishon. All right, similar to the ASK. All right, so output is reversed when a symbol 0 is being sent. Okay, so symbol 0 is being sent. That means your Y1 will consist of noise plus the carrier component, right? And then Y2 will only have noise. Yeah. So in general, right, the probability of error for non-coherent detection of FSK signal is half of e to the power of minus a square over 4 sigma square. All right, and we compare this with non-coherent detection. Non-coherent detection is Q of A over root 2 sigma. All right, if you compare these two, again, for non-coherent detection, the probability of error again is slightly worse because it's bigger. It's slightly worse. Again, this is only true for small value of A over sigma. All right, if you use a bigger A over sigma, all right, then these two numbers are pretty close to each other. All right, and then PSK. All right, basically PSK, as for PSK, is impossible to do non-coherent detection. All right, so just to have, again, just to have a comparison with PSK modulation techniques, we are going to use the DPSK. We are going to use a DPSK for comparison, all right, for non-coherent detection. So the probability of error for DPSK signal is half of e to the power of minus a square over 2 sigma square. All right. So now we compare with the coherent detection for PSK. you see that again, DPSK performs slightly worse as compared to PSK. All right, and this is for coherent detection. This is for non-coherent detection. Okay, so this slide show you the comparison in graph, yeah, as well as the bit error rate in table. Yeah, now let's look at what we have studied about these three modulation techniques so far. So for the first three are for coherent detection, and then the last three here are for non-coherent detection. Yeah, then you can see for coherent detection of ASK is Q function of A over 2 sigma. All right, and the probability or the bit error rate plot, all right, of Q of A over 2 sigma, all right, basically is this graph over here. This graph. All right, that's for coherent ASK. And then FSK also fall under the same graph. Why? How is it possible to have FSK fall under the same graph? Because we are using the same the average signal to noise ratio. All right, we use the average signal to noise ratio. Therefore, they will have the same graph. Okay, that is for coherent ASK and FSK, and we compare to PSK here. All right. Again, you see that for PSK, yeah, this graph. Again, for let's simply take one signal to noise ratio over here. This is 5. All right, with the same power. All right, the coherent PSK will give you a lower probability of error. All right, as compared to the coherent ASK and FSK, which give you a probability error somewhere around here. Yeah. And then if we were to compare with the non-coherent, all right, so for the non-coherent, let's say DPSK is here. So DPSK will give you this probability of error. So again, it's worse than coherent. Yeah, DPSK is non-coherent, right? So it's slightly worse than coherent. Yeah, but it's a bit better than the coherent ASK and FSK, right? Because it's lower. Lower mean better, yeah. And if you compare with non-coherent ASK and FSK, in this case, it's the worst one. All right, with the same power, it only give you this probability of error, the highest probability of error over here. Okay, so now this is how we actually compare them using the same power. All right, and if you were to compare them with the same probability of error, so if I want to get the same probability of error for these few modulation scheme, so therefore I have to draw a line here. All right, draw a line here. Let's say I want the same probability of error of 10 to the power minus 3. All right, how much power do I need? How much power do I need if I actually detect using PSK? How much power do I need to have at the receiver? All right. So if you look at the coherent PSK, I need the power of this here. About, shall I say this is 5, this is 7.5, we say close to 7. Yeah, 6 point something to 7 dB. All right, but if I were to send using this DPSK, if I were to send using DPSK, so I need this much power, signal to noise ratio, which is maybe about 8, I would say, 8 dB, right? And then the same probability of error, if I were to send using, now this graph is for what? Coherent ASK and FSK, right? Coherent ASK and FSK. So I require the signal to noise ratio to be close to 10, which is about 9, I would say. Here. Yeah. And if I were to receive, if the receiver is receiving using non-coherent ASK and FSK method, then the signal strength at the receiver need to be this much. The signal to noise ratio need to be this much, maybe about 11 dB, I suppose. Yeah. So you can see if the performance is of the modulation scheme is not as good, so in order to achieve better bit error rate performance, so you have to increase the signal power. Okay, so therefore, so these are the two comparisons that you must be able to make in your discussion. All right, in your discussion for your assignment later. Okay, any questions so far? So this one is for what? Coherent PSK. All right, and this one is the DPSK, the power required. All right, and this one is for coherent ASK and FSK. All right, and then this one is for the non-coherent ASK and FSK. Okay, so that is yeah, the discussion on the bit error rate performance of these few types of modulation schemes. Okay, and detection method. Question? No question? No question, then I move on, yeah? All right, so we can see from the graph that non-coherent detection basically retain the same hierarchy of performance compared to the coherent demodulation techniques. Yeah, you can see that as far as error performance is concerned is worse. The non-coherent demodulation technique performs slightly worse. But if you were to increase the, okay, again, this graph again, you only show it up to 12.5 dB. Yeah. But if you actually increase the signal to noise ratio, meaning you increase your signal power, you can see that this graph, the coherent and non-coherent graph, okay, will get closer and closer to each other. All right, therefore, the non-coherent detection method will actually, performance will actually approach the not coherent method at high signal to noise ratio. All right, and then as for non-coherent demodulator, they are easier to build as compared to coherent demodulators. So we'll talk about this in chapter 7a. So we can always refer back if you need to clarify this statement. Yeah. All right. So now, shall I talk about error rate and simple error rate? I think I'll leave this to Wednesday. Okay. So any questions so far before I stop the lecture?
No question.
No question. So clear. Good. What is average SNR? Average SNR. Okay. So as far as all right, so ASK, ASK we actually look at, you see when you transmit ASK, we transmit with what do you call that? We transmit with a 1, we transmit with a carrier, right? 0, we transmit no carrier, right? Yeah. And then for FSK, FSK we actually transmit 1 with one frequency, right? We transmit 0 with another frequency, correct? Yeah. So the average SNR is actually meaning that we actually transmit ASK and FSK with the same signal power. All right, the average same average signal power. All right, same average signal power in ASK and FSK means for ASK you need higher amplitude. All right, for ASK you need higher amplitude. Why is that? because the ASK, when you transmit ASK, you only have power when you transmit 1. You don't transmit any, you don't actually transmit a power when you transmit 0. No power is used. All right. So therefore, the average power is, the power when you transmit a 1 with the average out the power that you transmit 0. So it's only half of power. Yeah. So in order to get the same power as FSK, you actually need to increase the amplitude so that you get the same power when you transmit ASK as compared to FSK. We're going to do this in a tutorial. All right. Okay. Then you understand that better. Does that answer your question, Jingwei? Okay, let me show something. Okay, for ASK, how does the ASK waveform look like? Like that, right? And then for 0, nothing, isn't it? Yeah. So for ASK, what is the power? This is A. This is 0. This is minus A. What is the power here? What is the power when a 1 is being sent? A square over 2, right? Sinusoidal wave. The power is what? The V peak over root 2, right? V peak over root 2, that is your RMS power. Then you square it, you get your power. All right, so there is A squared over 2. And what is the power here? 0. Correct? So what is the average power? Average power is this one plus this one divided by 2, right? So your average power is A squared over 4. Yeah? And then for FSK, how you send a 1, how you send a 0? You send a 1 using high frequency. 1 cycle, 2 cycle. You send a 0 using low frequency. Right? Again, amplitude is A and minus A. So what is the power here? A squared over 2, right? So here is also A squared over 2, right? So now what is your average power? A squared over 2, isn't it? Right? So that means in ASK and FSK, you actually send them using the same carrier amplitude. For ASK, you're going to get half of the power only, half of the average power as compared to FSK. All right? So when I talk about same average power in that slide, I mean that you also need to transmit your ASK using A squared over 2, your power. All right, you also need to transmit at A squared over 2. So how to get A squared over 2 here? So meaning you need to transmit at A squared. The power need to be at A squared, right? So when you transmit a 1, your power need to be at A squared. And then you transmit a 0 with no power, that will give you an average power A squared over 2. Correct? So now if I want the power of A squared, then what should be my amplitude here? What should be my amplitude here? Vp is A squared, right? So where's my Vp? Root 2a, isn't it? Right? So I need to transmit my ASK signal, all right, with the amplitude of root 2a as compared to FSK, I use a can already. All right. Okay, so if you actually transmit your ASK with the amplitude of root 2a instead of a, so that means your Q function now, your Q function now is actually what? Root 2a over 2 sigma, isn't it? Correct or not? So that will give you a Q function of a over root 2 sigma, which is the same as the Q function for FSK, which is the a over root 2 sigma. Okay, so that's how the coherent ASK and FSK detection we can use the same curve. All right, provided we actually transmit ASK signal with the average power of same as the FSK average power. And to do that, we must transmit our ASK signal with the peak amplitude of root 2a. So you substitute this root 2a into the amplitude or the equation for the Q function for ASK, then your A now become root 2a. Right, so therefore you get the same equation as the FSK Q function. Okay, Ken. Ken, you have to, if now you have to, you turn on your mind and tell me once I stop sharing, everything is gone. I'm not going to copy everything again. I'm not going to rewrite everything again. Yeah? Quiet means okay, Silent is consent. Okay, so I'm going to stop sharing and I'm going to stop this one as well. Oh, no mic, okay. All right, okay, good. Okay, so any more questions? If not, then we're going to end the class here. No question? Okay. Good lah. So make sure you actually go through this chapter and understand whatever that I've discussed, because you're going to need this in your coming practical session as well as your assignment. All right, so you really need to understand this chapter. Chapter 7a, chapter 7b are to be used for your assignment. Okay. All right, so then we end the class here then. Yep.